question. Okay, well, let's start. So let's do the unit conversion problems. You can see here my first problem. I say convert 100 kilometers per hour to MKS. And in this course, we're going to use MKS units. And there are like several different dimensions that you can measure. Like you can measure length, you can measure time, you can measure mass, and you can also measure this thing information, which entropy. If you're a chemistry major or biology major, you can measure entropy. But in this course, we'll only need the first three. And for measurements of length, we'll use meters. For measurements of time, we'll use seconds. And for measurements of mass, we'll use kilograms. Not grams, but kilograms. Okay, and so let's do this first conversion. The way you do these problems, and this is a kind of a foolproof method, is you identify what units you have to convert. And so here I have to convert from kilograms to, sorry, from kilometers to meters. And the reason is that kilometers or kilometers are a measurement of length. And we don't want to work in kilometers for our measurement of length. We want to work in meters. So that's the first conversion. And what you need is a conversion ratio. Okay, and so the way I like to do this is I pick the bigger unit, which is 1 kilometer, and I say, okay, 1 kilometer, how many meters is that? Now, you do need to know the metric prefixes, which most of you have seen, and even if you haven't, I'll be introducing them as the course goes along. There's not a lot that you need, okay? Next semester, you'll need a lot more than you need this semester's, but you'll need a few. Kilo, that K there means 1,000. So you get this 1 kilometer is equal to 1,000 meters, like that. And that will take care of this one. Okay, you'll see how I make use of that in a second, but let's do this one next, hours. That's a measurement of time. And for time, we don't want to measure in hours, we want to measure in units of seconds. So you say, okay, what's the bigger unit? Well, obviously at 1 hour is bigger than a second. And you say, how many seconds are there in an hour? Well, there's 60 minutes in an hour and 60 seconds in a minute. So 60 times 60 is 3,600. So 1 hour is 3,600 seconds. Now, what you're going to do with these is you're going to make ratios. Okay, if I take 1 kilometer and I divide it by 1,000 meters, like that, you can ask yourself, what's that equal to? Well, if the numerator is equal to the denominator, that has to equal 1. I mean, like if you divide 3 by 3, that's equal to 1. 5 divided by 5 is equal to 1. So 1 kilometer divided by 1,000 meters, because those two are equal to one another, that's equal to 1. Okay? You can also make the fraction the other way around. And in other words, I could take this and flip it around. All right? Like this. So instead of the kilometer being in the numerator, I can move the kilometer to the denominator. Okay? And this is still equal to 1. All right, you'll see why I'm looking at both of these in just 1 second. Okay, so you can make two fractions: 1 kilometer divided by 1,000 meters, or 1,000 meters divided by 1 kilometer. They're both equal to 1. Same thing with the hours here. Okay, so I could do 1 hour divided by 3,600 seconds, and that is equal to 1. Okay, and I won't do the other one. The other one would be 3,600 seconds divided by 1 hour. Okay, now, how do you use these? Okay, so I apologize, I can't do like, like because this is just a text editor. This you just have to know this is in the numerator and that's in the denominator. I can't make the vertical line there. But what I'm going to do is I'm going to multiply by 1, and you can always multiply by 1 and not change a value. But I'm going to pick one of these two to multiply by, such that the kilometers cancels out and it's replaced by meters. Notice that here the kilometers are in the denominator, and here the kilometers are in the numerator. So I'm going to pick this fraction here, like that, and that's what I'm going to use for my 1, like that. And the reason I did that is, see here, that's kilometers in the numerator, there's kilometers in the denominator, they'll cancel in a minute. If you had used the other fraction, then they won't. Okay, and so that's why I gave you both of them, and you have to decide which one to choose. All right, then for the hours here are in the denominator, so you want the one with the hours in the numerator, which is this one here, like that. Okay, and if I multiply this out now, what will happen is the kilometers here, I'll actually remove them. The kilometers here will cancel the kilometers there, and the hours here that's in the denominator will cancel the hours there like that. Okay, and what you're going to get is basically just 100 times 1,000. The meters didn't cancel out, so that survives. Okay, and the seconds didn't cancel out, so that survives. And so you're going to get 100 times 1,000 multiplied by 1 over 3,600, and that one equals, I've done this so many times I've got the answer memorized, 27.8 meters per second. Okay, so this is the same as the one that I did during the lecture, but I think there, if my memory serves, I think I did 50 kilometers per hour rather than 100 kilometers per hour. Okay, so there it is. Let me just take a look in the chat, and wait, statement 15. I'm just reading what I have here in the chat. I don't know what this one statement is here. Yeah, I don't know who this person is that's asking questions. So, Rajiswari, I'm sorry, but this is a private class right now, so I'm not sure you're in the right place. All right. Okay, guys, let's go on to the next question. I don't see any questions from our regular students here. And let me go on to the next question. Okay, if there's no, if you have no problems with that one, let's go on to the next one. Okay, here. Okay, so this one is another conversion problem, but it's different than the one I did in class. Here, I have 7,500 cubic centimeters, and a cubic centimeter is basically a measurement of volume. Volume is like a length times a width times a height. Okay, and in this particular measurement, I'm doing the length, width, and height measurement in centimeters. But that's not MKS units. In MKS units, you'd want meters by meters by meters. Okay, so a meter cubed would be your volume measurement. And so, how do you convert that? Well, you realize that you've got meters. You want to go from centimeters to meters, and you begin with the larger unit. 1 meter is equal to 100 centimeters, like this. Okay, and again, you need to know that a centimeter is the MKS prefix, or sorry, the metric prefix that means 100th. So a centimeter is 100th of a meter, and so 1 meter is equal to 100 centimeters. You could also use the other one. You could do this, like 1 centimeter is equal to 0.01 meters, and both of them would work perfectly fine. But I like expressing the larger unit in terms of the smaller unit rather than the smaller unit in terms of the larger unit, just to avoid these fractions here like that. Okay, and so now that you have this fraction, you say, okay, well, I've got centimeters in the numerator here. Let me put centimeters in the denominator. So I do 1 meter divided by 100 centimeters. Remember, this fraction here is equal to 1, okay, because 1 meter is equal to 100 centimeters. And that is correct. That's the way you want it. But it's not enough, because you see here you have centimeters cubed. Now, I can't do a superscript 3 in this in my text editor. So this little caret here, this up thing, is how I'm going to do exponentiations when I lecture to you. Okay, so centimeter cubed is 3 centimeters. It's like a centimeter times a centimeter times a centimeter. And so you could rewrite this as centimeter, centimeter, and centimeter, like that. Now notice I multiplied by this fraction here like that, but I've only got 1 centimeter in the denominator. That'll only cancel one of these. Okay, so I need to actually multiply it by I need to multiply it by that fraction 3 times. The first time, this fraction here will cancel out the first centimeter. The second centimeter will be canceled out by the second one, and the third centimeter will be canceled out by the third one. Okay, so unlike the previous example where I didn't have any exponents on the units here like that, here I have an exponent cubed like that. And so for each of the units there, for each of the centimeters, you need to convert it to meters. And so since there are 3 centimeters here, centimeters cubed, you're going to have to multiply it by the conversion factor fraction 3 times. Okay, and well, let me just show you how they cancel. This centimeter here will cancel against that centimeter, This centimeter here will cancel against that centimeter, and this centimeter here will cancel against that centimeter there like that. Okay, and let me just quickly do that on my calculator. I think I know what the answer is, but divided by. All right, like that. And notice there's a meter, there's another meter, and there's another meter. So you have meter, 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 and 3 meters is meters cubed. And that's your answer. Okay, let me take a look here in the chat, see if there are any questions. I'm not seeing any questions, guys, so I'm just going to continue. I'm going to just continue with the next problem. I should just say that we're not going to be working with volume this semester. That's something more next semester. But we will have units which are squared, like we'll have meters per second squared, okay, as an example. And there'll be other squared units in there. And so there will be occasions, even this semester, where you'll have to convert units which are either squared or cubed and so on. All right, let's go on to the next one. Now, to be honest, I'm not going to be working with like pounds and inches and so on this semester. But I do want to show you that this method works no matter how, no matter what units you have, even if you're going like between non-metric system units or whatever, okay? And so what I want to show you is how you can use Google, if my browser will behave here. I'm having a little bit of technical difficulties with my one browser. Oh, there it goes. It's up. Okay. Let me just show you how you can use Google to do to find that conversion fraction. Okay. So here I've got pounds, and of course pounds is a measure of weight, and that's like mass. We'll talk about the difference later. But we want to convert from basically pounds to its MKS equivalent, which would be kilograms. And you say, well, what's the relationship between pounds and kilograms? I mean, you don't know what that is. So what you can do is you could just use Google, and this is how you use Google to do it. Let me just switch to my, all right, there you go. Just in like google.com, you just put convert the one unit to the other unit. So convert pounds, LBS. You could have even written out the word pounds there. So convert pounds to kilograms, and it'll immediately give you that fraction, okay? And so it says here that 1 pound is equal to 0.453592 kilograms, okay? And so let me just cut and paste that number over here like that. So 1 pound is equal to kilograms like that. Oh, let me switch. Let me switch back to my other window here. Oops. There we go. Okay. So now you should see my whiteboard again. So I've got 1 pound is equal to 0.543592 kilograms. And once you form that that equivalency between the two units, you can form the fraction that you need. And what fraction do you need here? Well, you've got 13 pounds like that. Okay. And so you're going to multiply, and you say, okay, how do I form this fraction? So you got a numerator and denominator. You want to get rid of the pounds. So you want to put pounds in the denominator like that. And you want to put kilograms in the numerator like that. And there you go. And I'll just do that very quickly on my calculator here. 0.453592 times 13. Oops, sorry guys. There we go. There's our answer. And that would be in kilograms. Okay. I think these kinds of problems are very simple, so I'm not going to do any more. I'm going to just look in the chat here, see if there are any questions. Okay, it doesn't look like anyone has asked any questions, so let me move on to the kinematics, because that's the more difficult and the more important stuff. Okay, so kinematics. The video that you watched was just general kinematics. Okay, we're going to be doing kinematics for some very specific problems starting next week. But for general kinematics, I had to define for you two different ideas for velocity and two different types of acceleration. There was the average velocity and the average acceleration, and then there was an instantaneous velocity and an instantaneous acceleration. Let's just look at the velocity. Okay, so an average velocity means how far did you travel in a given amount of time, where that given amount of time is a finite amount of time. So a typical question is like, how far is Niagara Falls, New York, and how long did it take you to travel? So Niagara Falls, New York is about 30 miles away, and say it took you half an hour to get there, and that would be traveling at about 60 miles per hour. Okay, so basically you would take the distance you traveled divided by the time it took you to travel that distance. Okay, and the ratio of the two is your velocity, but it's an average velocity because the time interval is a finite time interval. It could be small, but it's a finite time interval. Average velocity needs to be distinguished from the instantaneous velocity. And in the instantaneous velocity, what you do is you take that delta t, that is the time interval, and you make it infinitesimally small. And infinitesimally small means calculus, okay? So basically, your delta x by delta t becomes a derivative. All right. And so the next two questions are meant to really drive that point home. We need to distinguish this idea of an average velocity and an instantaneous velocity. To be honest, for the rest of the course, the instantaneous velocity is going to be much more important than the average velocity. But right now, we do need to know about an average velocity. Again, instantaneous velocity is the velocity at an instant in time. And to get that, you have to use calculus. That'll be question 5. But the average velocity, that's just, how far did you travel divided by the time it took you to travel that. But where the time that it took is some finite amount of time. All right. So let's do a problem to show you how that works. A car is found to be at the following positions at the given times. Okay. So you're actually going to do this kind of an experiment in the lab. And there you'll have like a linear air track, and there'll be a glider which sits on top of the linear air track. The air track has like these little holes, and air comes out of them, and it forces the glider to float on top so that it glides along without resistance, without friction. And what you'll do is you'll actually look at where the glider is at different points in time. You'll actually use the computer to help you do that, okay? Here I just made up some numbers. I said, let's imagine that there's a car driving down the street, okay? And it's at these positions at these times, okay? Now, the position is measured with respect to some reference, which I didn't tell you what that was in the problem. But if you go back to my lecture, that would have been like a tree. I chose a tree. So you say, you know what, this tree, that's going to be my origin. And every time I make a position measurement, it's always how far is the car from the tree? How far is the car from the tree? You don't want to change your reference around, otherwise, you get confused. So all throughout this problem, whatever the reference here is, whatever that origin is, stays consistent, okay? And so at t equals 0 seconds, so you've got like a stopwatch, and right now the stopwatch says 0 seconds, and the car is at 2.5 meters from the tree, from the origin, okay? And then at 1 second it's at 3.1 meters, and then at 2 seconds it's at 3.9 meters, and then at 3 seconds it's at 4.9 meters, okay? So these are like 4 data points at which the car is at a particular position with respect to the tree. Okay, I've got 4 questions here. The first one is, what's the average velocity during the first time interval, which is 0 to 1 second? Okay, so that's from 0 to 1 second there. And then 1 to 2 second, then 2 to 3 seconds. And then I said, you know what? Give me the average velocity over the whole trip. These are average velocities because presumably the car was somewhere between 0 and 1 second, but you don't know where it was. Like, where was it at half a second? You might guess that it was in the middle there, like between 2.5 and 3.1, but where? And even that's not guaranteed because the car could have moved forward very fast and then moved back, okay? So these really are average velocities. They're not instantaneous velocities, and there's no way you can get an instantaneous velocity out of this data because in no way you can there's just not enough data to shrink that delta t down to 0, okay? That process of shrinking delta t down to 0, it's fundamentally a limit, and that limit means that you're taking a derivative. Again, we'll see that in question 5, okay? So let's just do this one. So what's the average velocity between 0 and 1 second? How do you do that? Well, the formula for the average velocity is v is equal to delta, and I can't do the triangular delta, so I'm just going to type out the word delta. Delta t divided by delta, delta x divided by delta t, like that. Okay. All right. Now, technically, I should put a little bar on top of that v because, an average velocity has that little bar on top. Again, I can't do that in this editor, but I think you got the idea. Okay. So delta x is like how far did you travel, and delta t is how long did it take you to travel that distance? All right. And let's do that. Okay. So delta x, let's do that first. All right. When you do a delta x like that, it's always the final position minus the initial position. Okay. It's like, where did you end up minus where did you begin? So at 1 second, where were we? Or where was this car? Well, at 1 second, the car was at 3.1 meters. Okay, great. So that's our final position minus our initial position. That is, where were we at 0 seconds? At 0 seconds, we were at 2.5 meters, like that. Okay. And there we go. So that's our delta x. That's how far we traveled. Final position minus the initial position, divided by delta t. Delta t is just how long did it take. Well, my stopwatch started at 0 seconds and went to 1 second. So my final time was 1 second. My initial time was 0 seconds for a time interval of 1 second. And if you do 3.1 minus 2.5, that's 0.6. And the units on top, meters, and the units on the bottom are seconds, so you get meters per second. So I did this all in MKS units. Okay, so let me look in the chat, see if there's any questions with that. All right, I know there's a bit of a lag, but if there's any questions, let me know. All right, so now let's do the next one. Okay, and let me see here. Okay, so what's the average velocity during 1 second to 2 seconds? Well, it's the same formula, okay, but now the numbers are different. So here we have the final position at 2 seconds. At 2 seconds, I'm at 3.9 meters, like that. At 1 second, that's my initial position, I was at 3.1 meters, like that. Okay, divided by the delta t, and the delta t is my final time minus my initial time, 1 second, like that. And if I just work this out, 3.9 minus 3.1 is 0.8, divided by 2 minus 1, which is 1, and that gives me 0.8 meters per second. Okay, so during the second of the journey, that is between 1 and 2 seconds. So my stopwatch, this interval started when my stopwatch said 1 second, and it ended when my stopwatch said 2 seconds. Okay, and during that time interval, my average velocity was 0.8 meters per second. Okay, you can see that I started during the first 1 second interval. I started off with an average velocity of 0.6 meters per second, and now during my second interval, my average velocity is 0.8 meters per second. Okay, let's do the next question. Same formula. I think you got the hang of it now. All right. This is going to equal delta x is going to be the final minus the initial. So my final is going to be 4.9 minus my initial position is 3.9, like that, divided by my delta t, which will be 3 seconds, my final time, minus my initial time, 2 seconds, and working that out, that's 1.0 meters per second. Okay, let me see if there's any questions. All right, don't see any questions. There's an exceptional amount of lag today. I'm not sure why. It looks like it's upwards of about maybe even a minute or a minute and a half. So I apologize for that. I've never had this big of a lag, but if you ask a question and you wait a long time, that's what's going on. Okay. Hopefully in the future, this lag will not affect future live streams. Okay. So here we have uh, our first our average velocity during our first time interval of 1 second was 0.6. Then that went to 0.8 meters per second, and then that increased to 1 meter per second. Okay. By the way, what's going on here, the reason I made the numbers do this is because the average velocity is actually increasing over time here. And whenever you have an average velocity that increases over time, you've got an increase, you've got an acceleration. Okay. So remember, the difference between velocity and acceleration, this is sometimes confusing to students. The difference between velocity and acceleration is velocity is just how fast you're going. Acceleration is how much you're speeding up. Okay, and you can see here that I was going at 0.6 meters per second on average. Then I was going 0.8 meters per second on average, and then 1 meter per second. Each time I'm increasing, like from 0.6 to 0.8, I'm increasing by 0.2 meters per second. And then from 0.8 to 1, I'm increasing again by 0.2 meters per second. So every second I'm increasing by 0.2 meters per second. In other words, I'm increasing by 0.2 meters per second, or 0.2 meters per second squared, and that's the acceleration here. I didn't ask you that in this problem, and I'm probably not going to ask you about average accelerations, because asking about average accelerations on top of average velocities gets really tricky. I'll leave that for the lab, but you should at least understand, what's going on with this average velocity. And again, just to remind you, this delta t is it's a finite time interval. Okay. In fact, it can be the entire duration of the trip. You might say, you know what, I'm not interested in my average velocity just during the first second or the second second or the third second. I want my average velocity during the whole trip, that is from 0 to 3 seconds, and you can do that. So it's the same formula again. Whoops. Like that. And now your delta x is from 3 seconds, the position at 3 seconds minus the position at 1 second. So at the 3 second mark, the car was at 4.9 meters, like that. And at the 0 second mark from our chart here, from our table, it was at 2.5 meters, like that. Okay, and so now our delta x is, again, you have to measure where were you at 3 seconds, where were you at 0 seconds, so the final position minus the initial position, divided by the entire time interval, which is now going to be 3 seconds minus your initial 0 seconds, like that. Okay, and if you work this out, it turns out to be 0.8 meters per second, like that. Okay, so there's the average velocity during the entire trip. Okay, now you should ask yourself a question. Does that make sense? Well, let's take a look at the average velocity during those 3 1-second intervals. Your low value was at the beginning, 0.6. Your high value was at the end, 1.0 meters per second. Your average has to be between those two. It can't be less than 0.6 because that's the slowest you were going, and it can't be faster than 1 because that's the fastest you were going. And in fact, it turned out to be 0.8, which is in the middle of the two. Okay, so yeah, it does make sense that over the entire trip, the average velocity is 0.8 meters per second squared. It's between the two extremes. Your average is always going to be between your low and your highest possible extremes. Okay. And looking here at the chat again, there are no questions. So let's go on. I think we go until 11:10. We'll finish in time. Let's go on to the last question. Okay. So here's one more question, and this one is about instantaneous velocities, okay, and instantaneous accelerations and so on. All right. So you have to use calculus for this, okay? So here I say, the height of an object above the ground is found to be given by this equation, okay? Now I didn't write in here x as a function of time. I can, okay? I just didn't do that, but basically on the left-hand side here, you've got x, but x depends on time. It's going to change over time, okay? And so here's a formula. Let me take that out of there because sometimes students think it means x times t. It doesn't. It just means x is a function of t. So x is going to depend on what time you have here, okay? And so let's answer the first question. This one should be really easy. How high is the object? Move that up a bit more. How high is the object above the ground at t equals 1 second. Well, that's exactly what x is. X is how high it is above the ground. So, it's a position. X is a position. And in this case, the reference point is ground level. And so ground level is x equals 0. And then you've got like a ruler up, going up vertically from the ground. And if you're up 1 meter, that's x is equal to 1, 2 meters, x equals 2, and so on. Okay. And of course, x changes over time because this thing is moving. And so this is going to tell you where it's going to be at t equals 1 second. And so all you have to do is just substitute t equals 1 there, like that. Okay, so let me take the entire formula like that. Okay, and over here, where is it at t equals 1 second? Well, that 1 second, that t there is 1 second, and this t here is 1 second, like that. All right, and now it's just a matter of calculating. And so 1 squared, okay, so that caret 2 is squared. 1 squared is 1, so the first term is just negative 2. 5 times 1 is 1. Sorry, 5 times 1 is 5, plus 10, like that. Okay, and that's going to be 13. Okay, like that. So this object will be 13 meters. We can just put a little English here. The object is 13 meters above ground level at t equals 1 second. Okay, like that. Now, I'm not going to do 2 seconds, 3 seconds, and so on. That was pretty trivial. It's just, take t and replace it with whatever your time is in there. Okay. The next one is where the calculus comes in, or the differentiation comes in. What do I ask? I ask, how fast is it going? Okay. Now, how fast, that's synonymous with the word velocity. So I want the velocity. But I don't give you a velocity function. I give you a position function. And you have to ask yourself, how do you get velocity? And in fact, it's not only velocity, it's the instantaneous velocity. Okay, how do I get velocity out of a position function? Okay, so the velocity is the rate at which x changes over time. So above, we had the velocity as this function right here. Okay, that's how I defined it above. But that's for an average. If you want an instantaneous, what you have to do, I guess you could say, you know what, I'm going to start with the same formula again. Okay, but now you have to make your delta t very, very small. In other words, an infinitesimal. Okay, and you say, well, how do I do that? I mean, how do you make delta t very small? Well, basically that is a limit. Okay, and if you take the limit as delta t gets very small, this turns into the derivative, like that. Okay, so basically you have to differentiate the function x. All right, so dx by dt, that is delta x by delta t, with the understanding that you've made delta t infinitesimally small. Okay, and I'll let your calculus teachers tell you about what infinitesimally small means rigorously in mathematics, but for our purposes, infinitesimally small means so small that it's beyond the limits of our instruments to tell that, if you made it any smaller, our instruments would not be able to tell that there's any kind of a change. Okay, now you can't do that up here. Remember with this, I mean, your time interval is 1 second. You can't make it half a second. You can't make it a 0.1 second. So you can't make it infinitesimally small. So you're stuck with an average with this table here. And even in the lab, you're stuck with an average. But here, because I gave you a function, you can differentiate that function. And now you have to know how to do derivatives. And maybe just very quickly here, let me show you that if you do the derivative of t squared, like this, with respect to t, all right, so here, let me just clean that up a little bit. So if you take t squared and you differentiate it with respect to t, you should know that the exponent here comes out in front, and the exponent decreases by 1, so you get 2t, like that. Okay, and if you differentiate dt with respect to t, like that, well, that one's kind of trivial because that's just equal to 1. Okay, so each term gets differentiated. Let me just rewrite that. This isn't the answer yet, but let me just rewrite that. This, when we differentiate that, that's going to be replaced by 2t. Okay, and this, when we differentiate that, that's going to be replaced by 1. like that. And this, when we differentiate that, when you differentiate a constant, maybe I should put that as my next line, the derivative of a constant with respect to dt is 0. Okay, and so when you differentiate the 10, that gives you 0 like that. Okay, and so you get as your function here, whoops, you get negative 2 times 2, that's going to be negative 4 times t plus 5. Okay, so that doesn't quite answer the question, but that does give you the velocity as a function of time. Remember, the velocity is the same as dx by dt like that, and that's going to equal, in this case, negative 4t. Now, I wanted the velocity at t equals 1 second, so the velocity at t equals 1 second, well, just take this entire function right here and replace the t with 1, and you get a velocity of 1. And so the velocity is 1 meter per second at t equals 1 second. Okay? Let me see if there are any questions in the chat. All right, I have a question here. How did you know it was instantaneous velocity for B? Oh, you know what? That's a very good question, because I didn't really specify. So I need to be very clear when I ask these questions, especially on a test or in your assignments. Okay, because we're doing this together, I pretty much said it's, we're talking about instantaneous velocity. Okay, so in the rest of the course, I won't keep saying average velocity, instantaneous velocity, because we'll almost always be talking about velocity. So if I don't say that it's an average velocity, assume it's an instantaneous velocity, okay? But for problems like this, I will definitely say instantaneous velocity, okay? How fast is it going also kind of implies an instantaneous velocity, because even if I hadn't said this, even if I hadn't said instantaneous velocity, how fast is it going at t equals 1 second? Notice I give you just 1 point in time, t equals 1 second. Over here, look at how I asked for the average velocity. I said, what is the average velocity during the 0 to 1 second mark? Or I could say, what is the average velocity from 0 to 1 second, or something like that, where I indicate that the time is an interval of time. Whereas here, I say, how fast is it going at 1 instant in time? Well, 1 instant in time is not a time interval. Therefore, even if I hadn't said instantaneous velocity, it's pretty clear that this has to be an instantaneous velocity, because I'm asking for the velocity at one time, not over an interval of time. Okay, at 1 point in time implies instantaneous. I hope that answers your question. Okay, like when I wrote this, I wouldn't say I was being vague. But, because we're doing this together, I wasn't very clear. I try to make my language incredibly clear on tests. So, if there's any possibility of a misunderstanding between average and instantaneous, I would definitely make it clear. But even so, if I ask for velocity at just 1 point in time, a point in time is not an interval, and so it must be instantaneous. Okay, you see if there's anything else in the... Phil, let me know if that answers your question. I can come back to it. Because of the lag, I want to do that last problem. And so over here, let's do the last one. What is the acceleration at t equals 1 second? So just like the average velocity is delta x over delta t, the average acceleration would be delta v over delta t. It's how much does the velocity change over time, okay? So, like remember in the previous problem, I said, look, you're going from 0.6 to 0.8 to 1 meter per second. You see how the velocity is increasing. So you're looking at the change in those two velocities, okay? So whenever you have a change in velocity divided by the time it takes for that change, that is an average velocity. To make that into an instantaneous velocity, well, you have to make the delta t infinitely small, so that's dv by dt, okay? So as soon as delta t becomes infinitesimally small, it's a d. That's how we indicate that in calculus, and that means differentiating, okay? So now you say, all right, well, let me differentiate. What are you differentiating? The velocity function, which is this one right here, okay? So this isn't the answer quite yet, okay? Let me go through it, and you see here, you've got the negative 4t. When you differentiate that with respect to time, dt by dt is just 1. So the dt by dt, that t there, that just gives you 1. Okay, I can write it in there. All right. And 5 is just a constant. And when you differentiate a constant with respect to time, that's going to give you 0, like that. That makes sense, right? Think about it. How much does a constant change over time? Well, it's 5 at this 1 second. It's 5 a second later. It's 5 a second later. It's always 5. So the change over time is nothing. Okay, so whenever you have a constant, the derivative of the constant is 0. And that's going to be negative 4 times 1, which is negative 4, like that. And that's it. So the let me just put that in there. The instantaneous acceleration is always negative 4 meters per second squared, okay? Even at t equals 1 second. Notice that the acceleration here, I could write it on another line here. The acceleration as a function of time is just negative 4. In other words, the acceleration doesn't change in this particular problem. I could have given you a problem if I had like a t cubed in there, then the acceleration would have changed over time. But I decided to do a situation where the acceleration does not change over time. And so the acceleration is always negative 4 meters per second squared in this particular problem. Again, the way I got that is I just started from my velocity function, which was negative 4t plus 5, differentiated that, and that just gave me negative 4 without any time dependency at all. Okay, and that tells me that the acceleration is a constant over time. So at all times, including I guess I said even here, probably including is better. Including at t equals 1 second, the acceleration is negative 4 meters per second. Okay,